At 6:54 in the morning, in a sky that seemed utterly routine, an F-22 Raptor fired a weapon the world was not supposed to know existed, a laser capable of destroying targets at the speed of light. This was not just another upgrade, it was a breakthrough that could upend air combat forever. But what followed was stranger and more consequential than anyone predicted. Engineers from Lockheed Martin's Skunk Works and the Air Force Research Laboratory faced a challenge. They had to fit a directed energy weapon into the tight confines of the F-22's internal bay without compromising stealth or handling. The pod they designed tipped the scales at 847 pounds, occupying space once reserved for missiles. Its weight pushed the limits of the Raptor's centerline bay, but it was within the airframe's structural tolerances. To feed the weapon, a 180-kilowatt generator was tapped directly from the twin Pratt & Whitney F119 engines, channeling raw power into the system. The generator's output dwarfed the standard electrical load, demanding new routing and reinforced wiring throughout the forward fuselage. The laser itself could deliver 150 kilowatts of continuous energy, a figure that, on paper, put it in the same class as some ground-based systems. One Skunk Works integrator described the installation as shoehorning a freight train into a race car and still making it run at top speed. The physical integration alone was a feat of engineering, but it was only the first step in making the weapon combat ready. The pilot's helmet display now offered 4 new icons: a ranging bracket, a power output meter, a thermal management gauge, and a beam accuracy cone. Each symbol translated the invisible world of high-energy physics into something a fighter pilot could read at a glance. The system calculated irradiance at the target, over 15 megawatts per square meter, a figure that dwarfed anything in the Raptor's usual arsenal. The beam itself, though invisible, had to remain perfectly focused despite the jet's speed, the target's movement, and the shifting air at 43,000 feet. Atmospheric turbulence, water vapor, and even microscopic dust could scatter or weaken the energy. To compensate, Altea's adaptive optics worked in real time, adjusting the beam's shape and direction thousands of times per second. The heads-up display showed the pilot exactly how much the atmosphere was distorting the shot. If the cone widened, the system would throttle, power, or shift aim to keep the energy on target. Every second counted, and every watt delivered meant more heat at the impact point. On this mission, the interface was not just a display, it was a live readout of the physics battle happening at the speed of light, high above the Gulf of Alaska. At 6:53 a.m., the radar warning receiver pulsed with a new signal. 62 nautical miles out, a contact appeared at high altitude, its track holding steady just above 50,000 feet. The system automatically tagged it as Hostile 1. The pilot glanced at the tactical display. Altitude, bearing, and closure rate all matched the profile from the mission brief. This was the Chinese-built CH-6 reconnaissance drone, brought here for one purpose: to be a test target. With a wingspan of 65 feet and a belly full of advanced sensors, the drone represented exactly the kind of asset adversaries would use to map out American defenses. Rules of engagement for the test were strict. No kinetic weapons, no radar locks that might tip off the drone's autonomous countermeasures, only the new pod, and only inside the designated range window. The distance ticked down on the HUD: 58 miles, then 54, then 49. At 45 nautical miles, the weapon selector clicked to DE. The pilot's gloved hand tightened on the stick. Everything was set. He waited for the geometry to align, then squeezed the trigger, launching a silent shot no adversary would see coming. At 9.2 seconds, a hairline crack traced across the CH-6 drone's left wing, captured in sharp relief by the chase aircraft's targeting pod. The laser's heat had overwhelmed the composite structure, forcing carbon fibers to separate and the internal aluminum spar to soften. As the seconds ticked by, the drone's flight became unstable. At 11 seconds, the pilot released the trigger, cutting power to the beam. The weapons bay doors swung shut, restoring the F-22's stealth profile. Less than half a minute later, at precisely 6:54 and 38 seconds, the damaged wing tore free from the fuselage. The drone spiraled downward, tumbling uncontrollably through the thin air. Its descent lasted 6 minutes and 19 seconds before it shattered on impact with the Gulf of Alaska. The cost for this engagement, just under $14,000 in electrical draw and coolant, stood in stark contrast to the price of a single IM-120D missile. On the radio, the test controller confirmed Splash 1 Hostile 1, that is a confirmed kill. Within 3 weeks of the test, maintenance logs at Nellis and Edwards showed a steady stream of F-22 Raptors rotated through hangars for classified modifications. Work orders listed only a project code, Advanced Airborne Defensive Systems Increment 4. The initial batch grew from 6 aircraft to 18 by the end of the quarter. Each jet returned to the flight line with a new bay-mounted pod and revised electrical schematics. Budget entries for the program appeared under generic line items, buried alongside routine avionics and software upgrades. No public statement explained the sudden uptick in depot activity. For those tracking tail numbers and sortie rates, a pattern was beginning to form. Within months, unexplained losses began to cluster along the northern Pacific. Reconnaissance drones vanished from radar without a trace. Surveillance balloons launched to test American airspace failed at altitudes no missile could reach. Russian Tu-142 crews filed reports of sudden sensor outages, wing pods and tail radars going dark in the middle of patrols. One foreign analyst quoted in a closed briefing called it a pattern of technical anomalies that defies conventional explanation. Today, directed energy weapons remain more rumor than reality, but every leap in technology reshapes the battlefield, often before the world notices. The next breakthrough may already be flying overhead.